let's go ahead and go over topic 1.4, composition of mixtures. And so basically what we're going to do is we're going to define what a mixture is, and we're going to discuss different ways that the mixtures can be represented symbolically and quantitatively. And so if you are looking in the textbook, go to pages 85 through 90. This is kind of an indirect correlation. It's going to go over more of it in the solution section, but we don't really have enough information yet to go into the solution sections in our textbook. So 85 to 90 indirectly in the textbook. So let's go ahead and talk about what a composition of a mixture is, like what are we talking about, and mainly it boils down to ratios. And so a mixture is going to be something that contains more than one pure substance, and what we're looking for is we're looking for the ratios of those pure substances. And so mixtures are going to have variable compositions depending on the pure substances that they can contain and the relative amounts of those substances. So again, ratios. And solutions are going to be the most common example of mixtures. Let's go ahead and take a look at what those. So let's go ahead and look at what that looks like. We have mixtures versus pure substances on here, and we have 4 different examples. And so if you look at example A, so example A, we have atoms of element X, and we also have 2 atoms of element Z bonded together. And so because we have 2 separate entities of these elements, container A is actually going to be a mixture, and the way that we are going to write that is X plus Z2. And if we go ahead and look at B, on B we have 1 atom of element X bonded to 2 atoms of element Z, and if you notice that's the same throughout the entire container. And so this molecule, since it's the same, is actually going to be representing a pure substance, and you can say that the compound is XZ2. If we look at C, we have 2 atoms of element Z, so we have a diatomic element Z bonded together. Again, it's going to be the same exact compound throughout, and so C is actually also a pure substance, and it's going to be the diatomic element Z2. Now, I keep saying this word diatomic. That just means that it exists with 2 of the same exact atom bonded together. And now let's go ahead and look at D. D, we have a single element X's, and we also have an element X bonded to 2 element Z's. And so because this is not exactly the same, D is going to be a mixture, and it's going to be a mixture of element X and the compound XZ2. Alright, so let's go ahead and talk about how this is going to apply on the AP exam. So it's going to mainly focus on the elemental composition of a mixture. And so basically, we're going to use the relative amounts of specific elements in it that can help us determine the pure substances in it. And so again, the elemental composition of a mixture can be used to determine the relative amounts of the pure substances that compose it. This is how we're going to see it turn up on an AP exam. And so what we're going to be doing is we're going to be doing elemental analysis, and that's basically going to find the relative mass of one or more of the elements in the mixture, and this is going to be used by chemists to determine how pure a substance is. So let's go ahead and look at an example to see if we can figure out what's kind of going on in these types of problems. So in this example, we have a 2.4 gram sample of a mixture, and that mixture is going to contain calcium chloride, or CaCl2, and sodium chloride, or NaCl. And this mixture is found to contain 0.12 grams of sodium. So the question is asking us what percent of this sample is NaCl. Well, we are given 1.2 grams of sodium. So that is what we are going to use. So this number is going to become important. This is where we're going to start with. If we have grams of sodium, what we're going to do is we're going to want to convert those grams of sodium into moles so that we can kind of convert between different substances. Again, we can't convert directly from grams to grams, but we can go from grams to moles and then moles of anything else. So let's go ahead and determine the moles of sodium just like we have been doing. And so we're going to use what we start with, the 0.12 grams of sodium. And we look at the periodic table and we find the molar mass of sodium. And so the molar mass of sodium is 23.0 grams. over 1 mole. If we go ahead and divide that out, we are going to get 5.22 times 10 to the negative 3 moles of sodium. I wrote it in scientific notation because it's a little bit cleaner than writing all of those zeros in front of the 5. The next step then is going to be to determine the moles of sodium chloride. And so if you look at sodium to sodium chloride, you're going to notice that there is 1 mole of sodium for every 1 mole of sodium chloride. All right, so it's a 1-to-1 ratio. So that means if we have 5.22 times 10 to the negative 3rd moles of sodium, we also have 5.22 times 10 to the negative 3rd moles of sodium chloride. And so to show this as a conversion factor, if you're not quite understanding that, we would go 5.22 times 10 to the negative 3rd moles of sodium. And what we would do is we would go 1 mole of sodium is the same as 1 mole of sodium chloride. And that moles of sodium would cancel out. And so you're left with 5.22 times 10 to the negative 3rd moles of sodium chloride. Now, the next step is going to be to determine the mass of the sodium chloride, because now we don't know the mass of the sodium chloride that we had. We have the mass of the sodium, but not the compound sodium chloride. So if we have moles, we can go from moles to mass. So we're going to start with our 5.22 times 10 to the negative 3rd moles of sodium chloride that we know that we have. And we're going to go ahead and try and figure out the molar mass of sodium chloride, which is we're going to add it up from the periodic table. And so when we add that up, we are left with 58.4 grams of sodium chloride is equal to 1 mole of sodium chloride. Our moles cancel out. When we multiply this out, what we are left with is 0.305 grams of sodium chloride. Okay, now again, this is like multiplying, so we're multiplying straight across. 5.22 times 10 to the negative 3rd times 58.4. And then the last step in these problems is to calculate the percent of the sodium chloride in the sample. So if we know that we have 0.305 grams of sodium chloride in the sample, all we're going to do is divide that by the total grams of the sample, which is 2.4 grams. And we're going to multiply that by 100 to get a percent, and you should be left with about 12.7% sodium chloride. Now, again, the AP test only has 1.4 significant figures, so you could leave it like this, but if this was a FRQ and this was a significant figure problem, you would not get the point for sig figs. You have to go back and figure out how many sig figs that you have. So this 2.4 has 2 sig figs, this 0.12 has 2 sig figs. So what I'm going to do is I'm going to round it to 2 sig figs, and so it's going to be 13% NaCl, and that's going to be your final answer. Alright, so let's go ahead and look at another example, and what I want you to do is I want you to try and do this example on your own first, so pause the video. It's exactly the same as the previous slide, except that it just has different numbers. So, a 5-gram sample of a mixture of calcium carbonate and silicon oxide contain 1.5 grams of calcium. What's the percent calcium carbonate in the mixture? And so the first step is to use what we're given. And so we're given 1.5 grams of calcium, and we're going to convert that grams of calcium into moles. So we are going to take this 1.5 grams. So we have 1.5 grams of calcium, and we are going to convert that into moles using the molar mass in the periodic table. And if you look at your periodic table, you should find that the molar mass of calcium is 40.1 grams. If you divide that out, you should get 0.0374 moles of calcium. The next step is to go from moles of calcium to moles of calcium carbonate, which is the entire molecule. Now, what you have to look at is how many calcium atoms are there for every whole molecule. And if you'll notice, there's going to be one calcium atom for every molecule of calcium carbonate. So it's just a 1-to-1 ratio, and so we don't have to really do anything, but I'm going to go ahead and write it out just so that you can get used to seeing how it would be written out. And so if you want to combine steps, you will be more than welcome to combine them. So you don't have to do this in sequential steps. You can kind of do it all in one problem. But since it's a 1-to-1 ratio, it doesn't really make a difference if you write it out. So it's going to look like that. Your moles of calcium are going to cancel out. And so you're left with 0.0374 moles of calcium carbonate. And then the next step is going to be to go ahead and convert those moles of calcium carbonate back into grams using the molar mass. Again, remember periodic table, add all the masses together. And so when you do this, you have 0.0374 moles of calcium carbonate. And you're actually going to multiply this one, so moles are going to go on bottom. So the moles cancel out. And you are going to put 100.1 grams of calcium carbonate on the top. When you multiply that out, you should get 3.74 grams of calcium carbonate. Once you have the grams of calcium carbonate present, you can find the percent of that by dividing it by the total mixture sample and multiplying it by 100. So calculate the percent of the calcium carbonate in the sample. Again, we're going to take the 3.74 grams of calcium carbonate, divide it by the total sample, which is given in the problem, which is 5 grams, multiply it by 100 to change it into that percent that we want. And when we do all of that, we should get 74.8%. Again, double check your sig figs. It looks like we're given 2 sig figs in the problem. So I'm going to round that up to 75% calcium carbonate. Final answer. Here's an example that you could see on a multiple choice question. So the mass percent of carbon in pure glucose, C6H12O6, is 40%. A chemist analyzes an impure sample of glucose and determines that the mass percent of carbon is 38.2%. Which of the following impurities could account for the low mass percent of the carbon in the sample? The first thing that you need to see is that the impure sample of glucose has a lower percent carbon than pure glucose. It has a 38.2 versus the 40% of pure glucose. So what we know is that the answer choice has to have something lower percentage-wise than glucose in terms of carbon. And so right away, that's what I'm looking for. And so the impurity, again, has to have a lower percent carbon than pure glucose. Well, just looking at the answer choices, which one for sure has a lower percent carbon than pure glucose? And the answer is going to be A, because water contains no carbon at all. So if it was present in the sample, it is going to decrease the percent glucose. And so water has to be correct. We don't really even need to look at the other ones because water will definitely decrease the percentage of carbon present in the sample. So the answer is A, water. Alright, so here's another multiple choice example. A student analyzes a 2-gram sample of a mixture of copper and aluminum by reacting the copper with nitric acid as represented in the equation above. So we have the equation above. The student determines that the reaction produces 0.010 moles of copper nitrate. Assuming that all of the copper in the mixture reacted completely, what was the percent of copper by mass in the 2-gram sample of the mixture? So first we need to determine the number of the moles of copper in the product. And so if you notice here, we are looking at a 1-to-1 ratio. And the reason that I got that is because we have one copper atom for the entire molecule. And so if we have 0.010 moles of the product, we have 0.01 moles of copper. So let's go moles of Cu. Okay, so now what we do is determine the mass of copper. And so we take the number of moles and we multiply it by the molar mass. And so we're going to set up our problem just to make sure that we don't multiply or divide wrong. And we have, if we look at the periodic table, it's 64 grams per mole of copper. So if we multiply that out, we get 0.64 grams of copper. Again, we're just moving the decimal place over once, twice. So that's how I got 0.64. And then we find the percent copper in the mixture. So we have 0.64 grams divided by 2.00 times 100, and this is going to give us approximately 32%. And if I look, 32% is an answer choice, and so B is going to be the correct answer. All right, so here's another question. And once we get further in the course and we talk about Beer's Law, you're going to automatically assume that this question is a Beer's Law question. It's actually not. It's actually a lot easier than what you're going to think it is. This is actually a stoichiometry problem. So a 0.630 gram sample of a mixture containing cobalt is analyzed using a reaction with nitric acid, which converts all of the cobalt to cobalt 2+. The cobalt 2+ solution is then diluted to a volume of 50 milliliters and spectrophotometrically analyzed at a wavelength of 510 nanometers to determine its concentration. The solution is determined to have an absorbance of 0.74. So I'm going to mark that on my graph right away. 0.74, it's going to be like right there somewhere. And so that's going to be the point that we are going to look at. All right, so now the graph shown at left is a calibration curve for the CO2 plus at 510 nanometers. Use the graph to determine the concentration of the cobalt 2+ solution. Calculate the number of moles in the 50 ml solution, and then determine the percent of cobalt in the mixture. And so, again, we are going to do this lab. It's a Beer's Law lab. We will talk about it a little bit later, but that's what you're going to assume this is. You don't really have to even know anything about Beer's Law to get this question right. You just have to be able to look at the graph and analyze it. So let's go ahead and take a look at what is going on here. So let's go ahead and break it down. If we break it down, we go from the 0.74 absorbance and we try and figure out the concentration. And so the concentration that I'm reading is going to be about 0.0131. And again, I'm getting that from the x-axis. I just dragged it straight down. And so that's going to be the concentration of the cobalt 2+ solution at an absorbance of 0.74. Again, you don't really need to know Beer's Law in order to be able to read the graph. Just read where the absorbance is that they're telling you, and then go and find the concentration. So now second, calculate the number of moles of cobalt 2+ in the 50 ml solution. Now this one's a little bit trickier because we haven't talked about molarity yet, but when we have a big M basically just means moles over liters. And so if we have a molarity problem and we're given milliliters, the first thing that we're going to have to do is we're going to have to convert that milliliters into liters. And so all we basically have to do is we have to move the decimal place over 3 times. And so 50 milliliters becomes 0.05 liters. So again, molarity is going to be moles of solute divided by liters of solution. We don't have it in liters, so that's something that we have to convert. And so if we go ahead and do that, it's going to look something like this. And basically all we're doing is we're moving the decimal place over 3 times. And so that would be the first step. The next step is going to be to plug it into the molarity equation. So if we're given a molarity of 0.0131, that's going to equal x, because we are trying to figure out the moles, divided by the liters, which is 0.050, liters, and so basically all we're going to do is we're going to multiply the liters on both sides to solve for the moles. And once we do that, we get moles equals 6.55 times 10 to the negative fourth. Again, I just multiplied 0.05 times 0.0131 to get moles based on the fact that molarity is moles of solute over liters of solution. And again, we're going to go over that more extensively later on. This is going to be very familiar to you. You're going to know what molarity means. This is just kind of a brief introduction to it right now. But again, molarity equals moles of solute over liters of solution. Most of the time, you're going to have to convert milliliters into liters for these types of problems because they're going to give it to you in milliliters. The next step would be to calculate the percent cobalt in the mixture. And so to do this, we have to convert moles to grams, just like we've been doing before. So if we have 6.55 times 10 to the negative fourth moles, we have 1 mole, and we're going to multiply that by 58.93 grams of cobalt. And when we do that, we are left with 0.0386 grams of cobalt. And we take that and we divide it by the total sample. And so we have 0.0386 divided by 0.630 that was given in the problem. Multiply it by 100 and we are left with 6.13% cobalt. Final answer. Alright, we got 2 more examples. Okay, next one. A 0.450 gram potassium supplement contains 22% potassium by mass. The potassium is present in the supplement as KCl with a molar mass of 74.55 grams per mole. And the question asks, how many grams of potassium chloride are in the potassium supplement? And so you're going to need your periodic table for this. The only thing that you're going to need on that periodic table is the molar mass of potassium. So let's go ahead and write the molar mass of potassium down. So the molar mass of potassium is 39.10 grams per mole. Alright, so now, to begin with, what we're going to have to do is we're going to have to figure out what we're dealing with here. And so we're given a 0.450 gram supplement, and we're given 22% potassium by mass. So this problem has one added step in which we have to figure out how much that is. So basically, what we're going to do is we're going to go 0.450 grams, and we're going to multiply it by that 22% to determine the mass of the potassium. And so if you do that, you should get 0.099 grams of potassium. So this is what makes that problem a little bit more tricky than the ones that we've been doing, is that it doesn't straight up give you the potassium mass. It gives you the percent. And so you have to kind of multiply that out to get the mass. Alright, so next we're going to convert exactly the same way. So we've been converting the mass of potassium into moles by dividing its molar mass. So we have 0.099 grams of potassium. And again, I wrote the molar mass up at the top as 39.10 grams of potassium for every 1 mole of potassium. And this is going to give the number of moles of potassium. And so now what we do is we don't want moles of potassium, though. Remember, we want moles of the whole compound, which is potassium chloride. And so if we look at potassium chloride and how it's written, it is KCl. And so for every one potassium molecule, for one potassium atom, there is one potassium chloride. And so I'm going to go ahead and write that as 1 mole of potassium gives us 1 mole of potassium chloride. But that's not what we want to end with either. What we want to end with is we want to end with grams of potassium chloride. And so what we're going to do now is we're going to convert those moles of potassium chloride into grams of potassium chloride. And so I'm going to put moles of potassium chloride at the bottom, and the grams of potassium chloride are going to go at the top at 74.55 grams. So now earlier I was talking about kind of putting it all together in one step, and this is what I was talking about. Now I don't want you to get confused. It's the same exact thing, I just haven't done the math yet. And so this was converting the grams of potassium to moles of potassium, and that was the step that we've been doing. And then the next step we've been doing is converting the moles of potassium to moles of potassium chloride, and so that would be this step right here. And then finally, the last step, step 4 that we've been doing is converting those moles, or actually this was step 3, is converting the moles of potassium chloride to grams of potassium chloride. So again, I just put it all in one math problem instead of having it in 3 different steps like we've been doing, but it's the same exact thing. And so what I'm going to do now is I'm going to multiply straight across and then divide top divided by bottom. And when I do that, I should get 0.189 grams of potassium chloride. And so now what we do is we do that last step. Actually, we don't have to do the last step. We don't have to find the percentage because that's not the question. It's asking us how many grams of potassium chloride are in the potassium supplement. And so we found it. This would be our final answer for that question. All right, so here is going to be our last example, and let's go ahead and this is an example of analyzing purity. All right, so you have a solid that you know is mostly NaCl. You suspect that it may have some NaI, some KCl, or some LiCl as well. When you analyze a sample, you see that it contains 73% chlorine by mass. Is the sample pure NaCl? If not, what else does it likely have in it? What I want you to do is I want you to pause this video and see if you can figure that out, and it will likely be useful to have a periodic table handy. So the way that we're going to approach it is by thinking of each of these compounds and figuring out the percent chlorine by mass. And so to do this, we're going to need to consider the molar mass of the various elements that make up these compounds. So looking at the periodic table, what I'm going to do is I'm going to write down all of the molar masses. So we have, first off, is sodium. So let's go ahead and write sodium's molar mass as 22.99. Okay, chlorine is going to be 35.45. Iodine is 126.90. Potassium is 39.10, and lithium is 6.94. All right, so let's go ahead now and let's make a table, and let's start with sodium chloride. So we're going to make a table. Let's go ahead and start with sodium chloride. And what we're going to do is we're going to find the percent chlorine by mass. And so what we're going to do is we're going to divide chlorine's molar mass, so that's going to be 35.45, divided by the molar mass of the compound. So that's going to be sodium's molar mass at 22.99 plus 35.45. And if I'm talking about a percent, I'm going to multiply it by 100. And what I'm going to get here is going to be the percent chlorine by mass of sodium chloride, which is going to be approximately 61%. So let's go ahead and write that right off to the side. Approximately 61%. Alright, so since the sample is 73%, it's much higher than 61%, it's going to be clear that the sample is not pure sodium chloride, because 61% is not what the problem is giving us. It's giving us 73%. It's a lot higher. So something with a higher percentage of chlorine by mass has to be mixed in. And so next, let's go ahead and consider sodium iodide. That's our next possibility, is sodium iodide. So we have sodium iodide. And if we talk about the percent chlorine by mass, well, it doesn't have any chlorine in it, so this one is going to be 0. So if we have something that has 0% chlorine by mass, that would actually drop the percent chlorine by mass that we would see in the sample instead of raise it. And what we're looking for is something that's going to raise it. So we can automatically assume that sodium iodide is out, not the right answer. And so let's go ahead and look at potassium chloride. So potassium chloride, KCl, and again we're going to do the same thing to find the percent chlorine by mass. We would go 35.45 and we would divide out 39.10 plus 35.45. Okay, so now what I want you to do is I want you to think about what happens in math. If we have a bigger denominator than we do in the original, that should actually decrease the number that we have, because the denominator is bigger, so the number is going to be smaller. Again, this is going to reduce the chlorine percentage because this denominator is bigger. So what I mean by that is this 39.10, okay, is larger than the 22.99 that we added up here in the sodium chloride. And so that's why this is going to be smaller than 61%. And so that's going to decrease. Again, we don't want to decrease it, we want to increase up to 73. So this can rule out potassium chloride. Okay, so now finally let's go ahead and check the last one, which is lithium chloride. And so if we go lithium chloride 35.45 and we're dividing it by 6.94 plus 35.45. I'm already feeling better about this because this 6.94 is going to be smaller than this, so that would decrease our denominator, and if we decrease our denominator, we're going to increase that percentage, and so we're increasing that percentage closer to 73. So your answer is going to be lithium chloride. I don't even have to do the math on this one as long as I understand what's going on with the math. So think about what's going on in the numerator and the denominator. The numerator is staying the same in all of these because we're trying to figure out the percent chlorine by mass. So the only thing that's changing is the denominator number, and as we decrease the denominator, the percentage chlorine by mass is going to go up. And so lithium chloride would be our contamination source in this sample.